Now, why does it not matter? Or why is it that we can actually just use these rises to construct the slope graph? Well, again, it comes down to the fact that both graphs are, at this point, unlabeled. So, I'll say that this works for any scaling at all. If we scale this graph, that implies a scale for this graph, and we'll do that explicitly in the next video. But the argument here is simply that since we're using the same, since these vertical lines are equally spaced, or at least they're supposed to be equally spaced, to the extent that we construct these lines at equal spacing, we have the same run for every triangle. Now, slope is rise divided by run. So, if this rise is twice this rise, then this slope is twice as great as this slope. And if this rise is 1.7 times this rise, then the slope here will be 1.7 times this slope, and so on. So that having the same run for every triangle, the slopes are in the same proportion as the rises. Now, there's no scale on this graph, so if I plotted the slopes versus the x-coordinates of the point of tangency, the graph would look exactly the same as it does when I just plot the rises. Now, when I say exactly the same, a graph through these points would represent the slope graph. A graph through these points that I obtained by doubling the y values at each of these x points also represents the slopes. The labeling I would use if I want to use this graph is different than the labeling I would use here. My y-scale would be only half as great, in a sense, as we'll see in the numerical example. But right now, you should understand a couple of things. First of all, that a graph through these points can be scaled to give you exactly the same information a graph through these points could, because the relative values of the y-coordinates are the same on both graphs, and those relative values are the same as the relative values of the rises of these triangles, because they all use the same run.